The starting functional group in this example is an iminium ion. This iminium ion, upon hydrolysis, gives a ketone where an oxygen has replaced the nitrogen. So that would be cyclohexanone. And the amine that is generated here, get my ring size right, would be this one here. The overall charge balance of this reaction would require that if I have a plus charge on the left side of this equation, then I need a plus charge on the right side of this equation. So I could say NH2 plus as the ammonium ion. And on the left side of this equation, I need a source of that oxygen. So that's my water molecule. This is a hydrolysis reaction. This reaction can be done under acid conditions or no catalyst, which is the equivalent of base conditions. Okay, so let's go ahead and start under conditions where acid is present. This iminium ion is already an active electrophile, and so the water can attack directly. If we have an acid as the catalyst here, we're actually going to be starting with the conjugate base of the acid for the reaction in this direction because we started with a plus charge on our reactant. So I'm just going to use a water molecule here. Here's my water molecule. The water is going to act as a very weak base, the conjugate base of a strong acid. And so here's that strong acid that is generated when I use water as a base. The next step, if I'm aiming towards explaining getting rid of the nitrogen on this structure, is that the nitrogen needs to get protonated. And so the nitrogen protonation looks like this, giving us a plus charge on the nitrogen. That nitrogen is now available to get kicked out. So here I am kicking it out. It's nitrogen neutral. And since I've balanced my equation by putting an ammonium ion there, I'm going to go ahead and use that as the base in this step. Ooh, that's an ugly looking bond. Let's make that a little bit cleaner. I'll redraw the whole ring. There we go. I'm gonna check, zoom out here, make sure I covered everything. If I'm labeling this as the acid conditions, I'm just going to point out that here is the acid and its conjugate base. So I'll put those labels in. This is You'll notice that since the starting material had a positive charge in it, our labeling for what counts as an acid, as acid conditions, feels a little bit backwards. Okay, speaking of backwards, let's do the reaction in the reverse direction. So we're going to come over here at the end, and we have a ketone. Here's the ketone. This ketone can react with the ammonium ion. That proton transfer serves two purposes. It makes the carbonyl more electrophilic, and it makes the nitrogen a valid nucleophile, because now the nitrogen has a lone pair. That nitrogen can then attack the carbonyl carbon. The nitrogen should still have a positive charge now. In the next step, we need a base, a very weak base, the conjugate base of a strong acid, because we're thinking about this being acid type conditions. So here it is, deprotonating the nitrogen. And that gets us our neutral hemiaminal structure. Which I had forgotten to label in the above scheme, but it's the same one. I'm checking as I go that all my intermediates are lining up. The principle of microscopic reversibility here, helping me to make sure my mechanisms include everything. Okay, the next step, I used water as a very weak base, and now I'm going to use its conjugate acid as a strong acid. Under acid type conditions, before I can kick out an oxygen, I'm going to protonate. That can now get kicked out as a neutral water molecule. So here's water leaving. And that gives me the iminium ion that I started with. Again, let's highlight the catalysis here that's happening. We're using a water molecule and a strong acid as the conjugate acid of that. And we can compare that now to conditions where we don't have a catalyst. Under conditions where we don't have a catalyst, the iminium ion is going to need to react with a hydroxide ion. So it might feel more normal to call this base conditions. Remember that since we're starting from a charged intermediate, the labeling seems a little bit strange. Okay, so here's the iminium ion. Ooh, let's try that ring size again. Double bond, 6-membered ring. So my hydroxide ion can attack that gives the neutral hemiaminal structure directly. The hemiaminal can get protonated at nitrogen by water, which was the conjugate acid of the strong base that we used. It's now ready to act as a leaving group, but under conditions where I have hydroxide present, I'm not ready to kick it out yet, because if I kicked it out right now, I would end up with an oxygen that has a plus charge in the presence of oxygen with minus charges. We're trying to avoid that in our mechanisms. So I'm going to take this OH group and I'm going to draw it out more explicitly so I can show its deprotonation. Here's the alkoxide, the negative charge, that's going to come help kick out the nitrogen. So I have a neutral nitrogen, and I have a ketone. And that's it. In the reverse direction, let's zoom back in here. In the reverse direction, if I start with the ketone, and the amine, the amine is a good enough nucleophile to go ahead and just attack the carbonyl directly. That creates this structure that has charges on both the nitrogen and the oxygen. If I'm going to be getting rid of that oxygen as a leaving group, I need to protonate it. Here it is getting protonated by a very weak acid, water. Before the nitrogen can help to kick out the hydroxide, it needs to get deprotonated. So here's the hydroxide ion, the conjugate base of the very weak acid that I just used. The hydroxide can deprotonate here. That nitrogen lone pair is now available. This is the hemiaminal structure. That nitrogen lone pair is now available to kick out hydroxide. Which gets back to the iminium ion that this question started with. Just zooming way out so we can compare here. Same iminium ion. The next example is an enamine, and this example is related to the one above it. We're going to look at the relationship between them. Here's the same product that we got in the one above. We've talked about different conditions, acid versus base, and this question is pretty open-ended, so there are a few different possible answers for as far as what the protonation state would look like on both the left side and the right side of this reaction. For example, if we're going to run this reaction with excess acid in water as a solvent, we might want to additionally, in this scheme, say here's our acid that will get used up, and in that case we would say, in fact, the product would be the protonated structure, the ammonium ion, under these conditions. So let's go ahead and draw that mechanism. The first step in this is for the enamine to get protonated at the alpha carbon. That's using the nitrogen lone pair in conjugation with the pi bond to protonate the pi bond. So here's the hydrogen that we just put on there. I'm not going to continue drawing it, but I wanted to have it drawn at least once. And we've made a nitrogen carbon pi bond. We have a plus charge on our nitrogen, so this is an iminium ion. Water can now act as a nucleophile to attack at the carbonyl carbon, the iminium carbon, breaking the pi bond toward the nitrogen, which gives it a lone pair, and creating the new carbon-oxygen bond. Now, I'd like to take a moment to stop and compare this structure. So in the example, the previous example, we had an iminium ion that we were starting with. And that iminium ion is the same one that we get after just a single step into this reaction. And you'll notice that in the previous example, we had some awkward naming of things. We were talking about using the conjugate base of the acid first, and then later using the acid catalyst. And in this example, you can see, because we started from actually the beginning of how this reaction would actually work, we've eliminated that awkwardness, because we've started from the acid, a strong acid. And so then when we go ahead and in the next step use the conjugate base of that acid, It makes a little bit more sense in this context here. So here's that step. At this point, our two examples have converged, so I'm not going to draw the entire scheme here. I'm going to say see above example. Next, we're going to take a look at the conditions for the hydrolysis of this enamine in which acid is not added. So this would be the no catalyst, or might be easier to think of it as the conditions where a base might be present. A hydroxide we'll see showing up in this mechanism. But the balanced equation uses the ones that were written in red originally. And I just circled those in blue so you can see where that is, in contrast to the green balancing that we did for the acid conditions. So we'll start with the enamine. And this enamine is in the presence of water. And water can act as a weak acid and get protonated or get deprotonated by the enamine. And we're looking at reaction at the pi bond, using the nitrogen lone pair to make a pi bond between nitrogen and carbon. That gives us a plus charge on the nitrogen. It puts the hydrogen at this location, and it also gives us a hydroxide ion. So we can say that even though we didn't add base to this reaction, we were thinking of it as a no catalyst reaction, we can see that base was generated during the mechanism. So the distinction between a base mechanism and a neutral mechanism is a little bit blurry for this reason. From here, this hydroxide is available to act as a nucleophile. And when it does, that creates the new carbon-oxygen sigma bond. It gives the nitrogen back a lone pair, and so we have a fully neutral structure, and this is the hemiaminal structure. Just like we did above, we're going to take a look and compare this to the previous example and see how it starts to clear up a little bit about how we were naming the reactants in the previous example. So here I'm zooming out, and we were thinking about up here this being a no catalyst reaction, but in fact we started with something where we added base to the mixture, and so that maybe categorized it as a base reaction. And here we called this a no catalyst reaction, and we started with just the water, the stoichiometric reaction, but we did generate the base during the reaction. So starting from the neutral enamine, the naming of this is a little bit clearer and a little bit more self-consistent than it was in the mechanism example where he started from an iminium ion. We don't need to draw the entire mechanism again because we can see that this hemiaminal structure is the same one that we generated in the first step above. We'll be doing exactly the same reactions from here on out. So I'm just going to write C example. See the example above.